A displacement current not only exists for if you have a dielectric with atoms or whatever that can be polarized, but also for free space. So there is something there, even if it's nothing. You know what I mean? So that's you have a part of that displacement current due to if you do have a dielectric and it has dipoles, then it's due to the dipoles. But it's also due to just the electric field itself, which is not so intuitive. Well, not at all, but that's just how it works. Okay, so if you do that, then the whole thing seems to work. Okay. We also have magnetic dipoles, but I think we'll leave that for a little bit later. Okay. So we'll just finish off today. There's one other bit that we have to include is point charges. Okay, so you could also have not just charges that are moving in a conductor, but perhaps moving in free space. Okay, they've been accelerated, perhaps in a cathode ray tube or accelerator or something like that. Then they also experience a force when going through a magnetic field. Okay. So and this is the Lorentz force. Okay. So perhaps you can consider that charge with velocity vectors a little bit of current, maybe. Okay, intuitively, but this is what it is. Okay. Again, it's at right angles both velocity and the magnetic induction field. Okay. So some similarity here. Okay, but it's something that needs to be included in the description. Okay, so if a point charge is moving in a region where both electric and magnetic fields exist, then experience a total force given by this Q times E, the E field, plus V cross B. Okay, so that's the Lorentz equation. Okay, maybe we'll just stop there. It's getting so we're up to Faraday's law of electromagnetic induction. Okay, so just stop there, and tomorrow we'll go on with that. Okay, and discuss this. Okay, so any questions on what we've had so far today? Anyone? Okay, anyone's EFA, did you have a question, or was it something from before? Okay, well, thanks for coming, and I'll see you tomorrow, hopefully at 10 o'clock, I think it is.